welcome back to Mind and Maths with Amina. Okay, so today we're talking about non-exact differential equations, also known as the why is this not working type of equations. Because honestly, we try to solve it normally. We check the derivative of m with respect to y and n with respect to x instead of matching like a happy couple. They're just not equal. They're arguing, they're incompatible. This is a toxic relationship. But don't worry, we are here to fix the relationship by something called an integrating factor. Basically, we multiply the entire equation by something that makes it behave and become exact again. It's like therapy, but in mathematics, and it actually works. So let's learn how to check whether our integrating factor depends on x or on y, because once you spot that, the whole problem becomes very simple. So let's begin by writing down our the format in which we get the question. It's going to be m xy into dx plus a function n of xy multiplied by the change of y is equals to a 0. So it is exact if and only if you take the derivative of m with respect to y and it is equal to the derivative of n with respect to x. If this happens, then you say that the equation is exact. But what if this condition fails? So suppose that this condition fails. So then we don't have exact equation. So this is not exact. So therefore we now have to fix this by finding something called an integrating factor. So okay, so suppose we find it. Mu xy is known as the integrating factor, and what we do is that we multiply this whole equation through by the integrating factor. So the integrating factor comes over here and then it comes over here again, and when you multiply it by 0 you just get a 0. So once you do this, the equation becomes exact, and therefore we solve it the usual way. Okay, so the question is, how do I find the integrating factor, like the mu xy? How do I actually find it? Okay, so the first step is find the partial derivative of m with respect to y and minus the derivative of n with respect to x over divided by the whole expression n, and check if it is dependent or basically a function of x only. If it is, then we use it as the integrating factor. So we make this expression into our integrating factor. And suppose that isn't a function of x, then we try another possibility, which is you take the partial derivative of n with respect to x minus m with respect to y, and you divide it through by the function m, and you check if it is a function of y only. If it is, then this becomes our integrating factor. And how does it become our integrating factor? I'll just write this over here. Mu x basically is e, the integral of fx dx. And what about the integrating factor here? The integrating factor is e integral of gy dy. And remember, we don't add a constant of integration over here. Okay, if this looks a bit overwhelming, let's just practice a question so this concept becomes clear. So let's just practice a question. And let me write down the question. So let's just do a practice question. Oh, again a mistake, but this time a spelling mistake. Okay, practice question. So suppose we have the following function mxy dx plus nxy dy is equals to a 0, with mxy being xy, x into y, dx plus y dy is equals to a 0. So first we're going to check for my exactness. Okay, that just has to be the step one anyways. So the partial derivative of m with respect to a y is an x, while the partial derivative of n with respect to an x is actually a 0. Okay, because this m is equals to xy and n is equals to just a y. As you can see, both of them are not equal to each other, so we'll claim that this equation is not exact, so we are a bit disappointed. Okay, so let's start by trying to find mu x. So let's do test for integrating factor mu x. And what was the test? It was that we find if we can see if we can find a function f of x. Okay, let's go ahead. So m with respect to y is basically just an x, and we have a 0 here over an n which was a y. This is a x over a y, and actually this is not a function of x, so we don't have a mu x. So therefore, okay, this wasn't a choice for us. So we're going to test now for an integrating factor, hopefully a mu y. So let's test for that. Let's try to find this. Okay, how do we go about this? We take a derivative of n with respect to x minus m with respect to y, and you divide it by an m. So we have a 0 minus an x over an xy, which is a minus x over an xy, and we get rid of the x quite beautifully. So we're left with minus 1 over y, and yes, this is actually a function of y. This is what we wanted. Okay, so what is our integrating factor? So mu y was the exponential to the power minus 1 over y dy, and therefore we have a e minus ln y, and we can write this as using the power rule as y raised to power minus 1. Therefore we get a y minus power minus 1, which is a 1 over y. Okay, so what did we have to do next? We had to multiply through by mu y. So we're going to have mu into m plus mu into n is equals to a 0, and I said that this becomes an exact equation and you can solve it normally. So what do I get? Let's plug everything in. A mu y is a 1 over y, and mxy was xy. Oops, I forgot to write dx here and a dy there. This is what happens when you teach extempore, which I am in a habit of. Apologies. Okay. And then you get 1 over y again, and n was, I think it was a y, yeah, a y, and is equals to a 0. So we get a x plus x. Why am I being so silly? Okay, this cancels out, this cancels out. So I get x dx plus dy is equals to a 0. And this is quite easily, like, it's easy to solve. First of all, it's become a separable equation. But even if I didn't see that, I could still solve it the usual way. But instead of solving the usual way, I can just write this as dy is equals to minus x dx, and then I can integrate. So I'm going to get y in terms of x is equals to minus x square over 2 plus some kind of constant, and I'll see the value at 0, and that's going to be c. So therefore y in terms of x is a minus x square over 2 plus whatever initial condition is given. And basically what we should have done over here is that we should have solved it the usual way, which is, I'm just going to do that quickly, that I'm going to say that m x y is a x here. So the partial derivative of m with respect to a y is actually a 0, and n x y is equals to a 1. So the derivative of n with respect to an x is a 0. So this, you can see, this becomes exact. Good for us. Now that it is exact, what I can do is I can say the partial derivative of f with respect to an x is equals to an x, and therefore when I integrate this, I'll have a f as a function of xy is equals to x square over 2 plus some any function which depends on y. Now if I take the partial derivative of f with respect to a y, I'll have simply the derivative of f small f. Oh, let's use some other letter, because it looks kind of weird if I put a f here and a f here. Let's just write an h. Okay, so the derivative of h with respect to a y, and we know that what was the partial derivative of f with respect to y? It was nxy, which is equals to a 1. So therefore these two need to be the same. So if the derivative of h with respect to y is a constant, what does this mean for hy? It's again a separable equation, and it's just easy to see that this is just going to be a y. Hence, therefore, our final solution becomes an f x y is equals to x square over 2 plus a y. And remember, we want to see the contour, right? So when we put f x y is equals to c, so this is, for instance, you can imagine this being an utility curve and this being an indifference curve. So when we put this equals to a c, we end up with the same answer as before, which was y in terms of x is equals to some constant c minus x squared over 2. So there you have it. That's it. That's how you take a stubborn non-exact differential equation and gently convince it to behave. The main idea is simple. It's to check who's misbehaving. Okay, so let's do a kind of recap. Okay, where did we start? Okay, here we go. So you want to check who's misbehaving. Okay, if they're not equal, no problem. Okay, they're not equal, no problem. We just multiply the whole equation by an integrating factor, which yes is basically mathematical therapy. So now that next time your equation refuses to be exact, don't panic, don't stress, just like it's okay, you know your integrating factor. It's very powerful energy. Anyhow, I hope this video was helpful. I'll attach these notes in the comment section, and that's it. Take care.